This is part 2 on our introduction to limits. And what we're going to do today, instead of taking a look and trying to figure out our limits by looking at an XY table, we're going to try and do it from looking at the graph itself. So let's say we want to find the limit as x approaches some number, I'll call it a for the notes, of some function, we'll call f of x. Here's how you're going to do it graphically. The first thing, obviously, is to graph it. Now, that might be like a book problem where the graph is shown you. It might be something you know how to graph by hand, or it might be something you graph like on Desmos or something. But get a picture of the graph. Once you have that, what I want you to do is draw in a vertical line right at the number that the limit is approaching. So if you're doing the limit as x approaches 2, go over to x equals 2 and put a vertical line there. Now, as far as the limit itself, what you're going to do is you're going to ask yourself, it's really two separate questions. You're going to ask yourself what happens as the graph approaches that vertical line, but it could be approaching it from either side, from the left side or from the right side. So this is what I mean when I say approaching, or to approach something. What you're going to do is you're going to pick a point on the graph, put your pen or your pencil actually on it, start tracing the graph towards that vertical line you drew in at the limit and see where it's going. Now, if the graph goes right to that line and just stops there, then the y value of the point where it stops gives you the limit for that one side. Now, if the graph turns either up or down and never touches the line, then we say that limit is either approaching positive infinity if it turns up, or negative infinity, and what we said in part 1 is we'll talk more about that later in the chapter. For now, we just say the limit does not exist. Then what you do is you repeat the test on the other side of the vertical line. So like if you did that on the right-hand side, you repeat on the left-hand side, because you remember it's two separate sides and each one can do something different. So here's what your answer could be. Number 1, your answer could be a constant, just a number. Your answer could be 10 or -7 or 0. Now that happens if both limits are approaching to the same point. And I'm going to draw two different pictures that are very similar that could show that. So let's say I'm doing the limit as x approaches 3 or whatever, I'll just make up a number. And my first graph is going to be just a continuous function that crosses right over the line. Now the second graph we want to look at, I'm going to do the exact same thing, but what I'm going to do is I'm going to put what's called a hole in the graph. And I'm going to say it crosses over the line, but you have that open circle, that hole on the graph there. Now, for both of those questions, the limit is the same answer. Because remember, one of the real important things we said in part 1 is when you're doing a limit, we don't care what happens on that line. We don't care what happens when x equals 3. We only care what happens when it's approaching 3. So let's do it one side at a time. Let's look at the left-hand side first. So what I said is just pick any point on the graph. I'm going to pick this point right here. And I'm going to trace it towards the line, trace the graph towards the line and see where it's going. So from the left-hand side, it's going to that point right there. And same thing on the other graph. Pick a point right here. From the left-hand side, it's going to that point right there. Now do the same thing on the right. Pick a point on the graph. It's going to the same place. Same thing over here. Pick a point on the graph. Trace towards the line. It's going to that same place. So for both of these limit questions, the answer would be the y value or the height of whatever that point is that it's approaching. Like maybe right here, this is the point. Let me just make up a number here. Maybe this point right here is the point 3, 2. Then the answer to that limit question would be 2. And maybe this point where I put the open circle, I called it a hole, maybe that's the point 3, comma 2. If that's the case, the answer to both of these questions are 2, because it doesn't matter what happens on that dotted line. It only matters what happens as you approach it. So both of these two questions have the same answer for a limit. It's 2 for both of them. All right. The second thing that could happen is you could get a vertical asymptote. So what I said is the answer would be DNE, or does not exist, if either side is going to positive or negative infinity. So for example, let's say that I'm doing the limit as x approaches 3 again. If my graph does something like this, let's say my graph is over here and it's twisting and turning, and then it turns up like that. Or it could have turned down instead of up, it doesn't matter which one. If you get that type of situation on either side of the line, the limit is automatically does not exist. It doesn't even matter what the other half of the graph looks like. The other half of the graph could have a limit. Like maybe the other graph goes like this, and it stops at this point 3, negative 3 or something. That doesn't matter, because if either side has this picture right here, or the same one, let me draw another one real quick. Let's say you have a similar picture, but it's turning down. You have that arrow pointing down. You have that picture right there. If you have either one of those, then the answer is does not exist. That's a vertical asymptote is what we call it. Okay, now the third possibility, I wrote on here, this usually happens if you're dealing with piecewise functions, but you can get what's called a step or a jump discontinuity, where it's not going to infinity, it's going back to the line, but in different places. And that would probably look something like this. So we'll do the limit as x approaches 3 again for our example. And let's say on the left side, it's going to this point right here. But from the right side, it's going to this, put a hole there down here. So see, both of these limits exist. Like let's say this is the point 3, comma 2, and this is the point 3, comma negative 3. So when you do the little tracing thing, if I pick a point over here on the left, and I trace, I go, okay, well it's going right there to positive 2. But then when I do it from the left side, if I pick a point on the graph and trace from the right actually, like I said, right and left backwards, but you get the idea. If I pick a point from the right and trace to the graph, I'm getting an answer. It's going to negative 3, but they're different. So if it's going to different places on either side, then again, just like the last one, we say does not exist for the limit. So the only way a limit exists is if both sides are going right to the same point, if they're meeting on that dotted line. And it doesn't matter what's on the dotted line, if there's a point there or a little open circle, what we call the hole, as long as it's going to the same place, then the limit exists, and whatever the y value of that point where they meet is the answer to the question. All right, so here's an example we're going to do together. And I'm going to give you several different questions, and it's going to match up. So like right here, first I said, what is the limit as x approaches negative 3? And then I said, what is f of negative 3? Meaning like without knowing the equation, without being able to plug in negative 3, just asking what is the function value there. So the key number I'm talking about right now is negative 3. And what we said for limits by graphs is as soon as you see underneath the word limit or underneath the letters LIM, as soon as you see x is approaching negative 3, just go to negative 3 on the x-axis and draw in this vertical line right here. Now, focus just on that dotted red line. What I can see is that the limit does not exist because it's different. It's on the left-hand side, it's going down to negative 1. And on the right-hand side, it's up somewhere about 0.6 or 0.7, something like that. But it's definitely a different place. It's doing this thing where, one is coming in low and one is coming in high. Now the second question is not a calculus question. It's more of like a math 3 question. Just saying, what is f of negative 3? Well, f of negative 3 is not about limits. It's saying what's happening on the line. So remember I said a limit is not asking you what happens on the line. F of negative 3 is. So all you're looking for is on that dotted red line, where is the actual point? Not the circle on the bottom, but that filled in circle up top. And I would say it's about, I'm going to approximate, I would say it's about 0.7. You know, basically, what is the height of this point right here is what I'm asking. Okay, let's do the same question for a couple more x values. So now I'm going to do positive 2. And again, I asked you the same two questions. What is the limit as x approaches 2? That's one question. And then what is f of 2? So let's go over to positive 2 and draw in our vertical line again. Now this time the limit does exist, because if you're doing your test, if I come in from one side, let's say I pick this point right here on the left, and I go towards the graph, it's going towards that point right there, and on the other side, it's going to the same place. So yes, the limit does exist this time. It's meeting at the same point, and the height or the y value of that point is the answer to the question. So for this one, I'm going to say it's about negative 0.5. Now the second question is the same as what we just did with negative 3, saying forget about limits, tell me what is happening on the line. And see that little point floating down there? That's the answer. And that looks like it's about negative 1. So I think f of 2 is that point there, the filled in point, which is at negative 1, but the limit, which is above it, is more about negative 1/2 or negative 0.5. Okay, same question for negative 1. So now negative 1 is the asymptote. You can see it. It's already drawn in. I'm not going to bother drawing in the vertical line. It's the gray one that's already drawn in. So basically, as far as the limit, we can see it's a vertical asymptote. And the way the graph is drawn, it almost looks like it comes together to a point. What it actually doesn't. What you're seeing there is two lines that are turning up and just going up forever. So this is going to be one of those where I said for now, because it's an asymptote, because those graphs are turning up, I'm going to say DNE. Later in the chapter, we're actually going to call that one positive infinity, but I don't want to get too far ahead of myself. Now the second question says, what is f of negative 1? I'm going to say DNE for that one too, because I don't see a point anywhere on that gray line, that gray dotted line. So I'm going to say DNE for both of these. Okay, let's do 0. Now 0, if you want to, you can kind of just use the y-axis, but if I wanted to draw in a dotted line, it's basically right here. Now 0, what I notice is this is what we call a continuous function. It's one of those graphs that just crosses right over 0. Now that means that this point right here, I'm going to call it about negative 0.6, that's going to end up being the answer for both of them. Because, number one, let's do the easy one first. F of 0 is just the point on the graph. And you can see on the y-axis right there, it looks like it's about negative 0.6. The reason the limit is the same is because as I come in from the left, it goes here. As I come in from the right, it goes here. It's going to the same point. So if you have a continuous function that just crosses right over the graph, those two answers are the same. The limit and the function value itself, the same point. Okay, last one, let's do negative 2. What color have I not used yet? Pretty much all of them. Let's go with a light blue. So here's my line for negative 2. Now what I notice is I think it's going to be the same as what we just did for 0. Because I have two graphs that it's kind of like two separate graphs. It's like a piecewise function that are meeting at the same place, but it does meet at the same place. So I think this point here, which is 0, is the function value. You know, that's right where the graph is. It's right on the x-axis. And if you look at limits, as I approach from one side, it's going to that same point. And as I approach from the other side, it's going to the same point. So I'm going to put 0 for both of those. The height of that point is 0. It's right on the x-axis. But basically, in the different examples we did, you saw a lot of different possibilities. So walk through them again one more time real quick. The first one we did in red at -3. That's what you call a jump discontinuity because it jumps from one point to another. It usually happens with piecewise functions, and the limit does not exist. The function value is wherever the point on the line is. Then in green, we had what's called the name for it is a removable discontinuity, but I usually call it a hole. There's a hole in the graph. Now the hole doesn't affect the limit, so we still had an answer for the limit there. That was -0.5. And then the function value is always the same question. Just on that dotted line, where is the point itself? And the point is just kind of floating there. So you can use that for the function value. Dark blue, we had a vertical asymptote. Vertical asymptote is going to be dne for both unless there's a point floating on the line like there was for the green one. In purple, we had a continuous function. Continuous functions are the easiest one. Both answers are the same. It's basically asking you what point is it when it crosses the line. And then the light blue one was the same as the purple one, but it was a little bit tricky. It shows you that not every piecewise function is a jump discontinuity, like our first one. If you have a piecewise function that are two completely different functions, but they meet in the same point, you still do get a limit value there. All right, I hope this helped you guys. I'll answer any questions you guys had from the homework when we meet in class tomorrow.